Welcome students, welcome to the next session of Fundamentals 1. So in the previous class, we have started our discussions regarding deflection of beams. There we have used McLeod's method, double integration method for calculating slopes and deflections for overhanging beams, simply supported beams and cantilever beams. And in the starting of the chapter itself, we have discussed one more method, that is moment area method for calculating slope and deflection for the beams, either for the simply supported or a cantilever. But in our syllabus, they are giving to discuss only the basic and simple loading cases for the simply supported beam and the cantilever beam. So, further, firstly, we will learn what is the meaning or what is the method involved in moment area. Okay? So, the moment area method, what it is saying? It is having two conditions. What is that? The total change in the slope between B and A is equal to the total area of BM diagram between B and A divided by the flexural rigidity. So, using the bending moment diagram's area, we can calculate the corresponding difference of the slopes between 2 points. Okay, maybe some condition I am having. So, it is saying, for example, if I am having a cantilever beam AB, okay, and when you want to calculate the difference between the slopes theta B and theta A, how the difference can be calculated? This difference of the slopes can be calculated from the area of bending moment diagram. So, for this structure, generation of bending moment diagram is very simple for us. We can directly generate the bending moment diagram for a cantilever beam with pointed at the free end with a complete hogging type moment of this triangle condition. Okay, so this type of triangular portion is there, and knowing this height, knowing this length, I can evaluate area of the bending moment diagram. Yes, we can evaluate, and the ratio of this area of the bending moment diagram divided by flexural rigidity, the multiplication of E and A. In the last classes of the slope deflection also we have mentioned this word, the multiplication of Young's modulus and moment of inertia. This E into I multiplication we call it as flexural rigidity. So this EI is called as flexural rigidity of the beam member. Okay. Now this difference is equal to 1 over EI by A, that is equal to theta B minus theta A is equal to A by A. Similarly, for the deflection also they should have to give one more condition, right? So, here A is area of the bending moment diagram between the points A and B, and also E into I is flexural rigidity of the beam section. So, this is for the slopes. How to calculate a slope at a point? For double integration method, we have considered a section. There we have equated the bending moment at a section is equal to the basic bending moment at a section formula, which is EI d square by dx square. And with the first integration, we have got the slope equation, and in the second integration, we have got the deflection equation. There we have got the integration constants, those we have evaluated using our boundary conditions. Now, in this method, what I am doing for evaluating the slope at a point or deflection at a point? So, for the basic conditions such as cantilever or the UD simply supported beam with a basic point rod and UDL cases, I am considering this moment area method, and there I can calculate difference of the slopes between these 2 points. Okay, maybe those 2 points may be there such as A and B. The difference of the slopes between those 2 points theta B and theta A, the difference of these two is equal to A by EI. Okay, so this ratio we have got, and this difference is my output. Okay, maybe this is the case they are giving me. Okay, theta A, what is the slope at the fixed end? That is equal to 0. At the fixed end, the slope is equal to 0. That's why as theta A is equal to 0 at the fixed end. Right? Now, I can write that theta B is equal to A by EI. So that's why only they have given use for the simple methods, simple loading cases. That's why I have chosen one cantilever beam. Okay. The next thing. So the deflection at B is the total area of bending moment diagram between B and A multiplied by the distance of the center of gravity of the bending moment diagram from B divided by the flexural rigidity. Again, the same thing. Again, we should have to use the same bending moment diagram area. Okay, we are having the bending moment diagram area and it is in between A and B for the original beam. And when you want to calculate the deflection at the point B, okay, deflection at the point B. So, y corresponding YB, how much I want to calculate. Okay, how we can calculate this YB? We can calculate using area of the bending moment diagram into distance of its center of gravity of the area of bending moment diagram from B only. At which point I am calculating the deflection? At that point only I should have to consider the difference, and from that point what is the distance of center of gravity of the bending moment diagram? That is x bar. So see here, it is multiplied by the distance of CG of the bending moment diagram from B. Okay, as I am calculating deflection at B. So at which point you are calculating the deflection? From that point, what is the distance to the center of gravity of the particular bending moment diagram area? Okay, that we will indicate as x bar, and it is wholly divided by E into I. So in the previous, difference of the slopes we have got as A over EI. Here, the deflection at a point is the corresponding bending moment diagram area, and the distance of its centroid, the distance of the centroid of center of gravity of the area from the point where I am calculating the deflection. Here I am calculating the deflection at B. That's why I am considering the point B as the reference. From B, what is the distance of the area I am calculating, and A into x bar by EI. Here also again they were explaining A is the area of bending moment diagram between A and B. X bar is distance of center of gravity of the area from B. At which point you are calculating the deflection? From that point you are calculating the perpendicular distance for the center of gravity of the bending moment diagram. Now we are going into 2 points. So from the moment area method we have got a small theorem which is Morse theorem. So the moment area method is giving some conditions, and using those things and with a simple method or a simple line we will get one more equation from the Morse theorem. Okay, so here the same points only here also they will be considering, okay, but they will consider for some cases. The change of a slope between any 2 points is equal to the net area of the bending moment diagram between these 2 points divided by EI. Yes, the same word, the change of slope between any 2 points is equal to area of the bending moment diagram between these 2 points divided by flexural rigidity. Yes, and also the next thing is the total deflection between any 2 points is equal to. So the deflection between any 2 points is equal to the moment of area. Area moment means A into y bar or A into x bar, like that. So the moment of area of the bending moment diagram between the 2 points about the last point B. So about the last point B divided by EI. So the difference, the total deflection between any 2 points, the total deflection between any 2 points is equal to what is the last point? If B is the last point, okay, from B, A into x bar from B reference, that is from the B reference divided by EI. This only they have given. The total difference between the slopes, the total deflection is equal to. So they have given the condition that the area of the area of the bending moment diagram divided by flexural rigidity is difference of the slopes between those 2 points. Similarly, the difference or the total deflection between the 2 points is equal to area moment of the bending moment diagram from the last point divided by the flexural rigidity. Okay, first for that I am considering some cases. Okay, the Morse theorem is conveniently used for some following cases. What are those following cases? Those cases are problems on the cantilever beam. Why the problems on cantilever beam? Why we can use that? So in the previous example only we have some theta B minus theta A is there. If theta B and theta A both are possible, like B will have some slope, A also will have some slope. If both are possible, still those two are unknowns only. if any one is becoming 0, I can directly evaluate the next value. So, in the cantilever conditions, theta A is always 0 as 0 slope will be at the fixed end. So, the only equation will directly give me the slope at B. That's why for all types of cantilever beams, I can use this Morse theorem because theta B minus theta A is equal to A by EI, and this theta A is becoming equal to 0 because at the fixed D there is no slope. So at the fixed end there is no slope. This is one case I am using for the Morse theorem. Next thing, simply supported beam carrying symmetrical loadings. So the simply supported beam having either UDL over entire length or center point load or UDL in the center span. So when you see the vertical section, the left segment should be like a same like the right section. That we call it as symmetrical loading. Okay. So the simply supported beam with the symmetrical loading also I can use for the Morse theorem. Why I can use this in the like previous? Here also one thing is there. So as the loading is being symmetrical, the deflection will be at the center, that is maximum. So as the loading is symmetrical, the center deflection is maximum and the slope at the center is equal to 0. In the last class itself we have discussed this point. So simply supported beam with symmetrical loading will cause maximum deflection at the center. So that point with the maximum deflection at the center will have 0 slope. So one point maybe it is C, it is A. So considering these two, theta A minus theta C, if you do so, this theta A minus theta C, this theta C becoming equal to 0 because at the center C there is no slope. That's why as this theta C is becoming equal to 0, only the final output theta A is equal to A by EI. So even though the equation is having two terms, even though the equation is having two unknowns, but once if I have took a chance that one of the answer is equal to 0, that's why this theta B directly can be evaluated. In this way I can solve because 0 slope at the center condition is also possible. And also beams with fixity at both the ends because at both the ends the slopes are 0. So wherever the slope is becoming 0, that point you can choose. So in cantilevers, fixity. In simply supported beam with symmetrical loading, center 0 slope. In the fixed beams, both ends 0 slopes. That's why these are the cases I can use for the Morse theorem, so that in the two equations, two unknowns, one of the unknown will be 0 directly and the remaining unknown can be calculated from the A by EI condition. Next, when you see any, if possible, see here, if any bending moment diagram is like this. So for this triangular section, you can calculate half into base into height. Like that, you can evaluate the corresponding area. And also, from the basic triangular principles, you can generate 1/3 of this, 2/3 of this. Like that, you can generate the center of gravity location. But in case of curved structures, like when a simply supported beam with UDL, what is the area of this portion? You can't remember because those are the things we learned from the previous of the mathematics condition. That's why we have given this part. So if you observe any section like this and that section is indicated as A1 and its center of gravity is a distance from this reference is indicated as x1 bar. Okay, so for such type of section, what is the area of this half portion and also what is the center of gravity from the tip? Okay, from the tip, what is the distance of the center of gravity? That we have written, and the answer A1 is equal to area of the parabola A, B and C, A, B, C parabola. So this may be A, B and C, and we are having the area of this portion as, if it is B and if it is indicated as D. So 2/3 BD is the area of the parabolic portion when it is coming like this shape. So this half like this semicircular like shape, this is not a semicircular, a smooth parabolic, and when I am calculating this type, so for this protractor half type shape I can evaluate the area. And also, what is the location of the center of gravity from the tip level? That measurement is indicated as x1 and it is 5 by 8 BD. Sorry, 5 by 8 B. So, that x1 is 5/8 of B. And also, when you observe any cantilever beam, and when you see a cantilever with a UDL over entire length, you can observe this shape. So, if this portion is B and if you know this dimension as D, what is this corresponding area A2 is 1/3 BD. See here, this was 2/3 portion and this remaining portion is 1/3 BD. And the corresponding distance of the center of gravity from this reference is x2 bar, which is equal to 1 by 4 times B. You should have to remember these terms because for the triangular section you can evaluate 2/3, 1/3 like that. But here for the curvilinear portion, then see here at the same time they are indicating these two curves. This quarter and this quarter they have indicated in the same picture. It is when a simply supported beam with UDL over entire length up to the center, the picture when I draw, this is L by 2 length. This is the maximum bending moment at the center. So, from this structure I am generating and I am generally calculating the area. And also, for the cantilever-like structure, when we got the curve like this and the remaining portion's area is 1/3 BD, this portion area is 2/3 BD. And it is having the centroid at 5/8 of B and that is having the centroid at 1/4 of B. Okay. So, in this way, you can evaluate the corresponding answers. And in the next thing, I am going for a loading case. Okay, so we have already said using a moment area method or Moore's theorem, you can generate or calculate the slopes and deflections for the simple cases. That's why I have took a simply supported beam with a point load at a center and I want to calculate the slope and deflection. Okay, so the first thing is a slope and deflection of a simply supported beam carrying a point load at the center. A simply supported beam AB is carrying a point load of capital W at the center. So, we have directly taken a simply supported beam which was placed like this and it is having a point load at the center. And also we have said for the simply supported beam which is carrying symmetrical loads only, we can handle with the Moore's theorem or the moment area theorem. Okay, and here what is the thing which is making us to do? Here the deflection is maximum at the center. As the deflection is maximum at the center, at that point the slope is equal to 0. So, in the slope equation, the point with maximum deflection will have theta c is equal to 0. Because as y is y maximum at the point C, the corresponding slope is equal to 0. So, this condition I can use in the generating slope at A, generating slope at B. Similarly, deflection at C also we can calculate. The next thing, so in review, what we need to do for calculating anything? Firstly, we should have to generate the bending moment diagram for the structure. So for the given loading structure, what is the bending moment diagram? Here I am having a point load at the center and the support reactions are W by 2 and W by 2, half of the total load. And we have generated the bending moment diagram and at the center I have observed the maximum bending moment as a W L by 4 and this one is L by 2 and this one is L by 2. So here I will solve for the left half. The right half I can indicate as the same symmetrical value because at A, what is the slope I can observe, at B also the same slope will be observed. Okay. So, when you see this, so this is our bending moment diagram and theta A minus theta C is equal to area of the bending moment diagram, area of BMD between A and C divided by EI. So, what is the area of the bending moment diagram between B and C? That is half base measurement is L by 2 into height is WL by 4 and which is divided by EI. And we have already said theta C is becoming equal to 0 as at the point C the deflection is maximum. That's why theta A is equal to W L square by 16 EI. So in this way we can evaluate the slope at this point. Similarly for the deflection also we can go. So when you observe we can say this WL square by 16 EI. So but the area of the bending moment diagram WL square by 16 EI. And the next thing is deflection. So at A WL square by 16 EI, similarly at B WL square by 16 EI. Now the next thing is using the Morse theorem I am calculating the deflection at the center C. As at point A deflection is equal to 0, I am considering at C. Okay. So YC, that Y is equal to AX bar by EI, and A is area of the bending moment diagram between A and C, which is WL square by 16, and X bar is distance of center of gravity of the area of the bending moment diagram between A and C from A, from the last point. Here I am at C point, I am calculating the deflection. So from the last point I should have to indicate the measurement. That's why in our picture also they have given that answer only. See here, whenever you are getting the thing forgot, so remember from this way only they measured. So here also for this triangle I am measuring from this picture. So the distance of the center of gravity also will be measured from this picture. So distance of center of gravity of the area A from A, which is 2/3 of L by 2. So the 2/3 of L by 2 which is equal to L by 3. That Y is equal to WL cube by 16 into L by 3 and divided by EI. As we have got the area WL square by 16 EI, as it is the same value without EI from the slope formula. So WL square by 16 into X bar, how much we have got? L by 3 divided by EI. So here I have got the deflection at the center of a simply supported beam with a point load is equal to WL cube by 48 EI. So simply supported beam with a point load at the center, its formula is WL cube by 48 EI. For the cantilever at the free end, it is WL cube by 3I. These two formulas we have used in our laboratory experiments also. Okay, the next thing is a simply supported beam carrying a UDL over entire length. For this case I am calculating the slope and deflection. Okay, so a simply supported beam AB of length L carrying a UDL W per unit run over the entire span. Okay, simply supported beam is there which is having names A and B, and it is carrying the UDL of intensity W per unit run over the entire length. Okay, and as the loading is being symmetrical, here also I can say at the center the deflection is maximum, and at the center point the slope is equal to 0, and the corresponding reactions are WL by 2 and WL by 2. Okay, now I am generating the bending moment diagram because in moment area method, in the name itself it is using area of the moment diagram, nothing but bending moment diagram. So moment area method. So using the area of the bending moment diagram, I will calculate the slopes and deflections. So once you see the bending moment diagram area, you can observe a parabolic structure. At the center I can observe WL square by 8 as the maximum bending moment, and we have already said this portion for this parabolic curve portions I should have to indicate the center of gravity for that 5/8 of the B. So 5/8 of B means for the center line, 5/8 of B means this base measurement. What is this base measurement? That is L by 2. So 5/8 of L by 2 is distance of center of gravity of this shaded portion only, not for the entire. Up to center I am considering because 1 is 0, 1 is the value. So at A I am having theta, at C I am having 0. That's why these two are the points I will consider. Right? Now, when you calculate the slope, okay, slope at A, considering the area of the bending moment diagram between A point and C point, between A point and C point, and using the original method and area of the bending moment diagram. See here, which one is L by 2, which one is WL square by 8. So, which is area of the parabola? So, 2/3. This is not a rectangle, not B into D. This is 2/3 base into height. So 2/3 L by 2 into WL square by 8. Multiplication I have got WL cube by 24. this is area of the bending moment diagram between A point and up to C point. And for the slope, that is A by EI, which is equal to WL cube by 24 EI. And the next thing is deflection at the point C. For the deflection at point C, what we should have to do? As we have said already, I should have to give the distance from A. Yes. So 5/8 of L by 2. As I am calculating deflection at the point C, I should have to measure the center of gravity of the area from the other end. As I am calculating deflection at this point, I should have to measure the distance of center of gravity point from the other end. Okay. So area already we have calculated, that was equal to 20 WL cube by 24. So area of the bending moment diagram between A point and C point into X bar. So WL cube by 24 area into X bar 5/8 of L by 2 divided by E into I. So in this way we have calculated a simply supported beam which is carrying a UDL over entire length. So from the bending moment diagram, so we have got WL square by 8 as the moment, and up to this portion only I have considered. Why we have considered up to the half? Because in our thetas, 1 should be equal to 0. At the center only I can get 1 should equal to 0. That's why I am using this condition, and this theta C is becoming equal to 0, as theta A minus theta C is equal to 0. So that is A over EI. Okay. So in this way we have got theta A as W L square by L cube by 24 EI, and YC is equal to WL power 4 by 48 EI. So this is the output for the next step. So WL cube by WL power 4 by 384 EI. So simply supported with UDL over entire length. And then the next thing is a cantilever beam with a point load at the free end. So a cantilever of length L is being fixed and the A end is free. So the cantilever is having fixity at the end A and the other end is free, and it is having a point load. As we have already said, for our moment area method I should have to use the area of the bending moment diagram. That's why I have drawn the bending moment diagram area. As we have said, 2 points, one should have 0 slope. That's why theta B minus theta A is equal to area of the bending moment diagram. Okay. Theta B minus theta A, which is equal to area of the bending moment diagram between B and A divided by EA. So the next thing is theta B, slope at B, that is dy by dx, that is at B, and area of the bending moment diagram between A and B is half into base into height. See here, what is this height? W into L. What is the base measurement? L. So half into L into WL. So half into L into WL, which is equal to WL square by 2 EI is the slope at the free end. Similarly, deflection at the free end we can calculate. That is YB A into X bar by EI. So this YB A into X bar by EI is equal to, as I am calculating deflection at B. So as I am calculating the deflection at B, then I need to measure the distance of center of gravity of the bending moment diagram from B as 2/3 of L. In case of simply supported beams, what is the other end? In case of simply supported beam, we are measuring at the center. So I should have to measure the distance from the other end. In case of cantilever beam, I should have to measure from the free end. Okay, I should have to measure its distance from the free end. Okay, so from the free end it is a 2L by 3. Area into center of gravity distance divided by A. In this way, we have got the answer as WL cube by 3A. And the next thing is a cantilever beam which is carrying UDL over entire length, as a fixity, as the cantilever beam is having fixity at end A and free end is at B, and it is carrying a UDL of intensity W per unit turn over entire length, and I am considering the bending moment diagram for this section as we already know, it is having a parabolic shape and it will have WL square by 2. Because W into L by 2, that's why it is WL by 2, and its length is L. Okay, so here also the combination of one 0 slope point and some point with some slope. So theta B minus theta A is equal to area of the bending moment diagram between B and A. So area of the bending moment diagram between B and A, what is the formula for this type of curves? That is 1/3 of base into height. So what is the base we have got? What is the base we have got? Base measurement is L, height measurement is WL square by 2. So this is WL cube by 6 is the area, and area of the Pentagon diagram between B and A divided by flexible rigidity is equal to theta B minus theta A. As theta A is equal to 0, directly theta B slope at the free end is equal to WL cube by 6 EI. So that slope at the free end is equal to WL cube by 6 EI. And then deflection at the free end. How we can calculate? That is A into x bar by EI. Again, x bar should be measured from the free end. Okay, from the free end it is at F. So for this curve we have said from this end it is 1 by 4 or the corresponding measurement by 4. And I have said I should have to give the measurement from this side. So that's why 3/4 of L. X bar is 3/4 of L. Why it is 3/4 of L? When it is a simply supported beam, when I am calculating deflection at center, I have measured the distance from the simply supported end. In case of cantilever beam, when you want to calculate the slope at the free end, I should have to measure its distance from the free end. So here I have got x bar is equal to 3L by 4. So A into x bar divided by EA. So that's why we have got WL power 4 by 8A. And finally, when you observe simply supported beam with pointed at center, theta C, theta A minus theta C, only theta A answer, A over EI, and YC, AX bar by EI. So here we have got WL cube by 48 EI. And then simply supported beam with UDL over entire length. Similarly, theta A minus theta C, as theta C becoming equal to 0, that's why theta A is equal to area of the Pentagon diagram between A and C, area of the Pentagon diagram between A and C divided by EI, and which is equal to, and also deflection at the center is equal to 5WL power 4 by 384 EI. So this is the slope and deflection condition for the simply supported beam with pointed at center, simply supported beam with UDL over entire length. When you see the next condition, a cantilever beam with a point load at the free end, W point load. So again I am having A point and B point. Here I can get the combination theta B minus theta A, as this theta A is equal to 0 and A between A and B divided by EI, which is W L square by 2 EI, and also this YB is equal to A x bar divided by EI, which is equal to WL cube by 3 EI, and then a cantilever beam with UDL over entire length, which is W per unit run, and also we have got theta B minus theta A, as at the fixity there is no slope, that's why theta B is equal to WL cube by 6 EI, and then the deflection is equal to A x bar divided by EI, which is equal to WL power 4 by 8 EI. So in this way we have calculated slopes and deflections for the simply supported beam with a pointed at center, UDL over entire length, cantilever beam with a pointed at the free end, and cantilever with UDL over entire length. This is the basic conditions we are dealing all over the chapter. Okay, so when you see the numericals, you can have the corresponding numerical values and you will solve for the slopes and deflections using double integration and mechanism. For the moment area method, they will give such type of conditions only, not go with the numericals more. Okay, so in the next class, we are going into the next chapter, which is thin cylinders and thick cylinders.